Okay, today's lecture is about sampling-based planning. The topics that we'll be talking about are here. So we will start this discussion as we did last time. If you remember, we were talking about discretized space, and then we were doing graph search. So this was our first method for solving a problem, the problem of planning. Then we also discussed a lot about configuration space, right? So this was last lecture. There was a lot of, well, concepts from topology, but it's not really like the point of the class, right, going into this. But you need to understand exactly what it means now that we don't live in this workspace, okay, where you have like nice coordinates. What happens if your mechanism has a rotation? If it has like different things, like for instance, rot in problem set 1, right? So this is an example of simple configuration space. We'll see that actually it's a very natural continuation of describing the configuration space and this discretized state space to go with sampling. We'll talk a little bit about, well, rigorousness on this. Yes, I think we have. Okay. So we'll see like some of the advantages of these methods. It's not as good. The guarantees are not as good as graph search methods, because if there's a solution, we are guaranteed to find one. We'll see that with probabilistic approach, with sampling-based approaches, this notion of guarantee gets a little weaker, but still it's very good. And then we'll see what is the price we are paying for this, right? So basically we need to do collision detection, and then we need now to explicitly define like what are these objects and look for collisions instead of just building the full configuration space, right? That's going to be very complicated for higher dimensions. Okay, and then two very popular techniques here. One is the probabilistic roadmap, and the second one is the RRTs. Both of them very, very famous techniques. Started like late 90s, early 2000s. With this, I would say that planning got like a leap in the kind of problems that it was able to solve, right? So there have been more breakthroughs since almost 20 years ago. But still, now with sampling-based, people were able to move on higher dimensional spaces and still have this in reasonable time. Okay, we'll talk a little bit about optimality when we are doing these kind of approaches, but very briefly. And other variants, I have uploaded some of these papers in Canvas. So if you want to take a look, you can take a look. If you like these kind of approaches, this could be an option for you for final project. Or if you're simply interested, I think would be like good literature read. Okay, let's get to this idea, right? We started last time just defining the configuration space as a continuous space, right? We were not talking there about discretization. But now let's imagine that we consider continuous state spaces, okay? So we know that these state spaces, we can also call them configuration spaces, right? If we are looking at how mechanisms move. We know that it could be very different, right? Some of them are topologically like more complex than just Cartesian coordinates, right? So this is what we are used to. Still, we might want to work with these spaces because this is the natural way of defining things. If you have a pose, we see that there's no other way. If you want to include orientation into your moving rod, you need to consider this. But I hope now that after problem set 1 that everyone kind of gets like good idea of what we mean by configuration space. Okay. So what if we just want to treat them as continuous variables, right? What if we have like all these state variables like here, right? So we have these two configurations, initial configuration and goal configuration. And what if we want to just say, look, we don't want, these variables are going to be continuous, right? So then the question is, how can we plan? So far we just know one technique, that is graph search, okay? So then the first solution that should come to all of your minds is discretize. Let's discretize, okay? You discretize like this. We have a regular grid. And if you have this, then we can apply E star or Dijkstra or any other graph search algorithm, right? So we know that this works, right? After problem set 1, I don't know, maybe your solution does something like this, okay? So I'm going to motivate why we want sampling based, just showing some issues, some little problems of this, right? And maybe some of you are already familiar with them, but the first problem is these parameters that we choose for discretization. So if you think about it, here, we as designers, we are putting a lot of information, like what is this step size? How can you know? Right? Maybe you try 1,000 times and then you come up with this value. Okay, that's good enough. But still, let's see what are the effects of these two things, right? So the first one is, let's start with this one, right? Let's say that we have two large discretization spaces. Take a look at this one. Take a look at this cell here, okay? So there's obstacles. Depending on how you calculate things, you are going to have a collision, right, exactly at the center of the cell. So this means that this discretization results in an impossible plan. There's no plan in this discretized space, right? You cannot follow like centroids of your cells and get to the final configuration, right? So this is a problem, but because we are living in a continuous space, we know that there's a solution, right? So what we should be doing is getting through this very narrow passage and just calculate a plan that is here inside, right? Our discretization resolution is not allowing for this. So I can say, sure, no problem. Let's just reduce the grid, right? Who would do this? You would, yes, I mean, that's reasonable. Why not? So what do we have then? Instead of, let's say, I don't know, this is, this is 100 or 10 by 10, right? Imagine that we simply add here another 0, and then we have 100 by 100 or 1,000 by 1,000 just by making things smaller. And then, yes, you can get here. In the limit, by the way, when you make this resolution to 0, what you have is a continuous space, right? Imagine you have infinite number of elements. This is kind of your space, and well, let's say that this is not what we want, because if you remember, graph search, what it needs is to search over all state variables. So if you have infinite, you are guaranteed to find a solution in infinite time. So it's not good, okay? Still, approximations of this are fine. But you also have a problem of memory, right? So let's take a look exactly on how it looks like. I'm adding here a little grid here, so it's just a smaller resolution. And if you remember, if we were using a very aggressive heuristic function, well, kind of the behavior that you should be expecting is the following, right? So you have your plan that goes like this. Now I'm in a very, very detailed grid space, right? It tries to get to the goal because this is what the heuristic is telling you, right? So the best thing is you go straight. And then what is happening here is that you need to escape these local minima, right? So basically you will need to, in this very small grid, by the way, you need to evaluate all these state variables, and then finally you will be able to escape the local minima, right? Because this is how the kind of queue works. You are just ordering your values, and it simply turns out that the best thing before you have explored all of them is just go straight. Just go to the closer one. This was what the heuristic was doing, right? Speeding up things. But if you have like a very detailed grid, then this might mean that escaping local minima is going to take a lot of checks on many, many states. Okay? So I hope now I have motivated a little bit. Discretization is good, but you need the right parameters, right? And this is usually very complicated. So let's consider now this second approach, that this is today's lecture, right? So fine, if you don't want to deal with hyperparameters, you don't want to try 1,000 times your problem, you don't want to think about, oh, am I going to have like an arrow passage close to like very coarse description, right? How to combine these things, this is usually not easy. If you don't want to deal with this, there's a very easy approach that it simply lets sample the space, okay? So the great thing about this, I'm just going to sample the space now. I'm sampling, by the way, the configuration space, okay? So although this looks like plain, you need to imagine that this is higher dimensions of whatever thing our mechanism or a system is representing, right? But I think it's simple just to start with saying that our configurations correspond to points in the plane, and then we'll not have like any trouble. We sample the full configuration space, okay? We come here, and you see that, well, there's little issues, right? For instance, yes, some of these samples are going to lie in collision, right? So we need to identify them. For that, what we were doing before is calculating this free configuration space and obstacle region explicitly. So we went there and we calculate for all the values that we have in our configuration, which ones were in collisions and which ones were not. So we can do this with convolutions or maybe other techniques. Here we are not doing that. We are simply sampling and then we don't know what's going to be there, right? And what is the great thing about this? You keep sampling, you keep sampling. Now imagine, I keep sampling, I do a lot of samplings here. The good thing is that the resolution adapts with the number of samples, right? So this is a little bit what we want. If you have infinite samples, you can imagine that you will cover the full space, right? If you're using the right distribution or at least sequence of points. If you stop earlier, still it's going to be okay, right? You're going to have a very detailed representation of your configuration space just because you will have a lot of samples. And then because we don't know which ones are in collision, we need a method that tells us when a configuration is in collision, right? And this is something that we will discuss also later in class today. Okay, so now this is the advantage of sampling, this adaptive kind of grid, if you want to think about it, right? And let's discuss a little bit. I still didn't discuss how these methods look like, right? We'll see later, but they are based on sampling, right? And this is more motivation, still, because we haven't discussed like the algorithms, we cannot really see. But this is the analogy. In discrete planning, we had guarantee completeness. Okay, so that means that we have all our states, they were discrete, and this is a set of states. Yes, no. They can be still infinite number of states, but as long as they are countable, guarantees on finding a solution hold, right? So this was a very strong guarantee. We don't have this, right? We don't have this now, but this was something very good because if there was a solution, it was guaranteed to be found in finite time, right? So yes, okay, so this is what we justify by saying that this is a systematic search, right? We just go over all the states and eventually if there's a solution, we'll find one. Now what happened is that we are changing a little bit. We are approximating this kind of discrete set of the states or configuration variables, if you want, to a set of samples. These samples, we don't know what they are. We might be lucky, we might be unlucky, but there's this concept of dense sequences that becomes necessary for us to guarantee that if we keep working on sampling, we are going to find good solutions. Okay, and this is very strong guarantee. In practice, doesn't happen because, well, this is kind of the caveat of this. These samples come arbitrarily close to any configuration as the number of iterations goes to infinity, right? So that means what I said. You can cover your full configuration space if you have infinite samples. This is not trivial. Okay, so the great thing about this is that, first of all, you need to use some specific family of sequences or random number generators, right? Not all of them are going to be giving you this solution. So you just need those that eventually they cover full space. But if we have this, then we can do this analogy to the discrete case. And then all sampling techniques are going to be by default with this notion of weakness instead of complete, what we call probabilistic complete. Okay? What is the motivation for this? As I said, if you go to the infinity, you have infinite number of state variables. And here is the same as having a graph search algorithm. The only problem is that you cannot solve that problem. You have infinite number of states, and it's not going to be solvable. But just for guarantees to finding a path, this is a very good way of going, right? So this will give us at least something, right? Okay, this part is more subtle, but I hope everyone agrees here on this, right? So if not, maybe it's time to discuss a little bit. Yes? Okay, so everyone is good with samples, right? We use this in many, many places. Why not here? Okay, let's discuss a little bit some of these alternatives for sampling, right? There's many, many of them. Grids are one of them. So remember, the only thing we want is that they are dense. We could start here with a grid. We could just kind of provide this as a sequence with different resolutions, and as the resolution goes down, we'll have this infinite number of sequences, and we'll cover all points that are available in this space. Lattices are the same, right? They are a little more efficient way of discretizing the space, and here we have this resolution, but if we keep decreasing the resolution of the lattice, at the end we'll have the same, a sequence that is dense. And for uniform is the same, right? So we have some infinite number of samples that we are drawing from a uniform distribution. In this case, I don't know, could be like 0 to 1 times 0 to 1. And the key point is that this is dense, right? It should be dense. What do you think? Oh, you have a question, yes. Sorry, what is the difference? You see the regularity that you are getting with the grid is a little bit different than the one that you are getting with the lattice. So it's built on a different way. So grid, you just take Cartesian coordinates, I don't know, your x and y, and then you just equally space center of your cells. For the lattice, well, you put like points, if you see, they follow like some order, but the formula is a little bit different. It's simply another way of covering the space. So you have some issues here, especially on diagonals, on the grid. Here, it's supposedly to be a little better. There's many ways of divide your space, by the way. So you have any kind of division. If it's dense, it's useful for you. What is what? A steady form. I don't understand this. Yes, I don't know about this question. So what is the distance around you are asking? Maybe write this on the chat. Maybe someone will ask. I cannot give you now exact number. Yes. Yes. This is a very good comment. So sampling is just another way of grid. as we are defining it, I agree. And it doesn't solve the problem if you go to infinity. But we only go to infinity for probable guarantees. So this is more a formal proof. If you go to infinity, you can solve the problem. If you have a large number of samples, you will solve the problem. Probably not. Yes, so it's more a matter of defining if you can solve the problem or not. If you have infinite number of samples, you can. But maybe you can stop earlier and still get a solution, right? So you will never get, on this kind of approach, you will never get to infinite number of samples. But it's giving you a guarantee that if you keep sampling, if you can keep kind of exploring the space, you will find a solution. And this is something that not all algorithms are giving you. So sometimes you start an algorithm, and maybe you don't know if this is going to stop. Yes, yes. The great thing is that with this, with grids, lattices, you need to start defining resolution, and this is a parameter that you need to tune. You either go down, but then what is the sequence, right? So it's a decreasing sequence, but how much? This is the problem. Sampling is just taking away this decision of the hyperparameters. You just choose a distribution or a sequence, and it gets automatically done for you. Okay, but it's a very good point, because one thing is formality of, okay, you can solve the problem, and the other is in reality, what are we gaining? So it's this, it's automatically, easily, a nice grid with good properties without tuning hyperparameters. Yes? Yes, van der Corput sequence is, I didn't explain it here. It's an example, another example of discretization of spaces. So the thing is that van der Corput covers this space very efficiently, so it starts with rough numbers, kind of dividing the space in big cells, and it goes into smaller cells. So imagine here you have this order. Imagine that I give you 10 or 5 sequences, samples, okay? So you will have this 1, 2, 3, 4, 5. You see, this is not very good representative of your configuration space, because the grid is ordered like this. Van der Corput will do something like this. So you start like this, you sample here, you sample, I think, here, then inside, right? So you go and you kind of do all this dissection, all these segments. It's just a procedure, systematic procedure, but at the end you get also a dense sequence. In Laval book, you will find more examples of van der Corput. Okay, what about Gaussians? Are Gaussians dense sequence? Right? No? What?
Only in the middle. Closer to the mean.
Okay. So let me plot a one-dimensional Gaussian. You mean if they are close to the mean, right? Right. So what means close?
I say 3 standard distributions.
Okay. So 3 sigma, if you're inside 3 sigma, you are saying that then we'll have a dense. So this is the other problem about sampling, that you could have an infinite space and still Gaussians, even if you are 100 sigma away, are going to give you like a dense sequence. But the number of samples that you need is so monstrous, so huge, that probably it's not what you want. So what I'm saying is that, yes, you are right, most of the probability probability mass is contained between minus 3 sigma and 3 sigma, but still it's not 0 on the tails. There's still some probability. And even that the probability is very low of sampling, according to our definition, it's still a dense sequence. So with this, you can cover the full space, R. Yes. This, what I want to say is that although you have a sequence that in theory is dense, it doesn't mean that it's good, right? So this one is like bad idea. Imagine you have here your sequence, your Gaussian, and you want to sample this. It's going to take forever just to get here, right? Or to other places. So having dense sequence is not the only guarantee. Once you have this guarantee, it's not like, okay, I'm good. I'm just going to forget about it. You need to think also like, well, how is this going to affect later? There are some solutions that use like this kind of approach, similar to important sampling. So you have regions that you know you want to sample more, and there's regions that you want to sample less, and some of these strategies are good. And the requirement is that as long as they are dense, it doesn't matter what you use inside, if they are one distribution or another. Okay. Yes. Now we have discussed a little bit about sampling. Let me take the second component. Oops. Yes, second component, that is collision detection. We talked a little bit about collisions, if you remember, when we were defining the obstacle region. So it was defined something like this. We say that all configurations that belong to our configuration space, if they intersect with an obstacle, that's part of, I mean, that configuration is in collision, right? So it's part of this obstacle region, as we were saying. If the intersection is 0, there's nothing that touches, then there's no collision, okay? So this is just a little reminder, but then the problem is going to be, how can we calculate really this configuration space? So another advantage of sampling is that we don't need to calculate the explicit construction of the obstacle region. So if you remember here, this is problem set 1. What we were doing is calculating an explicit calculation of the configuration space just by having all values, all possible values. They were discretized, by the way, so we have discretization in X and Y and in theta. We were discretizing them, and then for all these possible values, all of them, we were checking if they were in collision or not, right? So remember, yellow is collision, blue is no collision, plus the borders, okay? Yeah, borders. We'll fix this, but we will not penalize. Okay, so that's the explicit representation. You go over all your configurations, all possible configurations, and you check if they are collision or not. If we have infinite number of states with continuous configuration space, that's not really possible, right? So what we can do is calculate an implicit representation. So what is going to be an implicit representation? What? This original image, this is your workspace? Yes. No, because what we are looking for is for the configuration of obstacles, the obstacle region. Okay, I'm going to give you a hint. We want sampling, and we are going to use the same principle as before. So we come here, we sample. Remember that this is a configuration, and that belongs to C. And each of these points, right, each of these points belongs to some workspace, right? So remember that obstacles belong to the workspace. I mean, they don't need to share whatever system you are doing. An obstacle, it's an obstacle here in the world. And then your system is doing whatever. It's rotating, it's changing. This is an abstraction for us. So what we can do is this. Here, this point is just the result of calculating this, okay? So you just place your obstacle in the world. And the key thing is that this is a continuous variable now. And now what we do is we apply this definition. This is just a definition. If before we were using just intersection as, okay, is any of your pixels overlapping with any of the pixels from the obstacle, right? So this was a definition. Now imagine that you have a continuous variable on your configuration. you just place whatever mechanism, because at the end they are not going to be points, they are going to be, well, physical entities, and then you check if there's a collision or not. So let me give like an example of this. We come here, yes, let's do this one, okay? So I'm placing here the rod, and this is, I don't know, 53 degrees, 0.3. Right? There's no need to discretize. You can put anything you want. You could be doing like this, right? So which is slightly. And here what we see that there's a collision. So when you sample this configuration here, you will see that there's a collision. The same happens here, right? So let's try to do it this way. Yes.
Do we sample with the kind of our object itself, or we sample with just the dots on panel?
Yes. Yes. So the question is, when we sample, do we sample with the obstacle or do we sample as dots? Every time that we work with configuration space, it's much convenient for us to treat points, to treat all variables as points. Right? There's no notion of what is an obstacle in the configuration space, unless we can calculate this explicitly. So what we have is a back and forth between you sample your point that represents some properties of your obstacle. Let's talk about rod, okay? So the rod is living in the plane at some position, and it has some orientation. With this configuration, configuration means position and orientation, you can plot the physical object in the workspace. So this is what I'm doing here. This thing belongs to the workspace. This obstacle, A, that is our robot, our system, whatever it is, this belongs to the workspace. So this is after, I don't know, you place your rod here. And this configuration here, this belongs to the configuration space. So this is just a way for you to place things. If you want to think about it, is once you give someone the coordinates, you just place it there, put the orientation, and that's it. And then what we do is we check if there's a collision in the workspace, because this is what we understand well, right? This is where objects live. This is where we can actually do this. Now the question is, we can do this for one sample. You need more of them, right?
So we just try to understand. We sample a dot in the implicit representation, and then we put our object to this dot and check if it's aligned with each other, but we do not make explicit representation. We can make it on the original environment.
No, the problem with the explicit representation is that you need to specify for all elements in your configuration space, for all elements you need to specify if they are in the obstacle region or not. And this is impossible to do when you have an infinite set. So the question is, what we are going to be doing now is we will approximate this obstacle region. Just by sampling enough of them, we know by the sequences we are using that they are dense, so we should be sampling all points. And in the limit, we'll have infinite number of configurations, some of them in collisions, others not. But if you just have a large enough number of samples, this is good enough. This is a good enough implicit representation of this obstacle region, right? So let me put it this way. You start like this, you start like this. Some of them are going to be in collision, right? Yes. Okay. So those that are in collision are just removed. Maybe in this guy, right? Maybe in this guy is removed. And with this, what we are creating is with this set of samples, it's going to be different every time. We are creating this implicit configuration space, free configuration space, right? Yes. Each of these samples has a different orientation, and it will depend on whatever sequence you are using. Right? No. There's no 4 rotations. There's infinite number of rotations now. Infinite number. So each of these samples is just going to give you slightly a different orientation. You have infinite, so forget about the 4 because I choose 4. You don't know, you cannot know. Actually, 45 is maybe not the best way of discretizing angles, so maybe we need it a little bit more. I did 45 because it's easy to plot in pixels. Yeah, but these kind of reasons should not be what is, making you decide if you use one or another. Each of these samples is going to have its own orientation because you are sampling in the configuration space. So let's say like this, yes, they are sampling from the configuration space, right? And then you don't know exactly what is there. The only thing you know is that once you have these configurations, you embed this into your system, call it rod, call it rocket, piano, whatever you want, okay? You put it on the space, and then you check if there's collisions or not. And obstacles, we understand that they are living in the world. We are living in the world, right? But there's other variables that are necessary, like orientations or who knows what else, that are simply not possible to be captured more easily. So sampling is giving an alternative. Okay, very good. Okay, let me see, because I think there's something missing here in this figure. Yes. Okay, so this is a little bit what I was saying, right? We have here our configuration space. Let me write it like this. This is the obstacle. Yes, obstacle. And then how we can represent this. So it's a little bit like this. Oh, let me use maybe another color. Yes. Okay, we come here, we sample here, we sample here. This thing, by the way, we don't know. We don't know where this obstacle lies because we don't have a way to represent this explicitly, right? So the only thing we can do is all the time check. So this is collision check, right? So we have this thing. Oh, okay. So the result of this collision check is collision. No, you're not good. Right? You keep doing this. No. And then we can say, if we cover the full configuration space, at the end, all these set of points that are not crossed are going to be our free configuration space. Okay? So this is a little bit the motivation. This is a very powerful technique because it allows you to go on automatic mode. You don't need to think too much. You don't need to take decisions like, oh, what is the step size? What is the discretization? These kind of things. Yes? This is another question, right? What is the connection between these, right? In this case, what we see is that some of them are going to end in collision and others are in free. So imagine this segment is kind of a set of more configurations, and you need to check if all of them are in free space, in the free configuration space. That means no collision. We'll cover this in a couple of slides, okay? But for now, I'm just talking about individual points. If you have infinite number of them, at the end what you have is a dense thing, where you think that everything is connected to its neighbor. We'll never make them dense. Reality is that dense is just a guarantee, right? So what we can do is establish criteria for connection. Okay? No, you first want to find a solution. So here, these configurations could be 6-dimensional. And for this, there's no hope to do any graph search. Right? Yes, like something Something like this, right? This we will cover in a couple of slides. So these are just techniques on how to do collision checking. But if you think about it, brute force is you just go and check many things inside each segment, right? Yes, but don't worry for this. For now, we are just describing this free configuration space as set of points. Yes. No. For now, the probability of finding a solution is only a consequence of comparing this with graph search. So this was the comparison. If you do a dense sequence and then do, let's say, graph search algorithm, graph search gives you like guarantees that you are going to find a solution. Now, what I'm talking about is if you just have a sequence, we want to know how the configuration space looks like. And instead of having like explicit representation, okay, you have this thing from x to 1 to x to, I mean, you get the idea, right? Instead of saying, okay, so this is the interval that is configuration space free and the other has an obstacle, instead of doing this, you forget about how to account for regions, shapes, whatever you want, and you just say, look, I have 1,000 configurations that all of them are free. This is your configuration space. This is how you are representing things. If you go to the infinity, you have infinite number of samples, then you can assume that they are connected and this is creating actually your space. But for us, it's like, what is your new representation? Instead of telling you exactly, oh, you have this that is free, this that is empty, you just give up enough samples, and this is going to be your free configuration space. Okay? Question you had? No? Okay. Almost the same. Got answer, I hope. Okay. We'll see in a moment like a couple of algorithms, and you will see how this applies. But the whole idea is just this change from explicit now to implicit. With points, you just have enough of them. You cannot even visualize, because who knows what is the dimensionality of this. Maybe each configuration is 10, dimension 10. But still, with enough collisions checkings, you have guarantees that, well, you have a good representation. Not totally accurate, but at least good enough of your configuration free space. Okay, so now what we need is collision checking methods. Okay, I'm going to do 5-minute break, and then we'll be back. Actually, yes. Now we will start with collision methods. So in 5 minutes, we'll be back. Okay, time to get back. We have discussed about sampling, its advantages. I hope now that everyone is convinced about this, right? It's a very powerful tool, and basically it allows you to use it without much specifications, hyperparameters, and all these things. Now the question is, the second component is collision detection, right? So this only works if we have a collision detection method that allows us to put our kind of system with the current configuration and then check if there's a collision or not, right? So then we basically do intersection with an obstacle. Well, this is an O. Okay, so the first thing is, well, we are getting more into technicalities, but there's multiple ways to represent objects. So at the end, all these things are physical entities. In the plane might be easier, but when we move to 3D, so we have different representation of this. Could be polyhedral, could be algebraic models, meshes, it's a very powerful one, sign distance functions, many of them, okay? So if you have worked with graphics or with others, maybe you know about this, but just for you to know that, look, there should be a lot. What we were using in 2D, it was just bitmaps. So what we were doing is just have an object, discretize, we use an image, and that's kind of a good enough representation. Okay, for each of the object representations, there is an exact collision checker, right? But still, it can be very complicated to calculate this obstacle region exhaustively, right? So this was the explicit representation. You go for all your states and calculate this, right? So this will be impractical. This is a little bit the motivation that we have also for sampling, right? So you don't want infinite number of samples, you just want some of them. The same happens for when you are checking if your configuration is obstacle region or it's free configuration space. Okay, if you want to go deeper into this topic, there's many things, right? I'm just here like writing like the most essential parts, basic ones. We'll talk about collision checking of very simple functions, but this can go like very deep. And the good thing is that there's many collision checking routines implemented, right? So maybe if you're using libraries, you don't need to worry about re-implementing some of them. I'm talking specifically about 3D and all these things, right? So collision is kind of a thing. Okay, so I'm just saying, look, there's a whole world there, but we will not be today. Take a look if you want later. Let's just define one of the simplest methods to calculate collisions, right? So it's based on these two steps. Again, this is not the only solution, right? There's many ways of calculating this. But in this case, a way of calculating collisions could be we describe broadly objects as boxes or spheres. I'm going to motivate now why we want this kind of very simple geometric objects, like spheres especially, right, and even boxes. And then we have a narrow phase. Once we have calculated like just broadly, then maybe we want to check for a little more detail. And in this case, this is just looking for maybe all polygons, all vertices in your model, or whatever you have, right? If the object is very complicated, sometimes this is the only way for doing. Okay, let's see a little examples about this, because I think it's going to be a little more clear. So again, this is another extra layer that I'm adding here, hierarchical methods. What we are going to be doing is add objects inside objects until we have a final big simple object, right? So example would be like this. We have this L here, right? Let's say we can approximate this with the spheres. So we have here sphere 1, 2, and 3, okay? So why do we want to do this? Because if we do a checking of some yes, well, okay. You know that this is, I'm checking the configuration, but actually what I'm doing is just calculating this, okay? So like kind of physical representation of whatever configuration it is. You check for this. And then you want to calculate what is the distance with respect to this. So instead of looking for all vertices, all things, all like detail, maybe it's so far away that it doesn't matter. Maybe the only thing you want to do is just do a single distance checking. And this is the great thing about the sphere. And this is going to be telling you, look, you're very far away, you are good, right? There's no need to worry. So this is just avoiding you to do a lot of calculations. If you are here, if you do this calculation, then you see the problem, right? So distance to 1, it's going to be smaller than the threshold. But then if you calculate distances to these two other components of your obstacle, are simply bigger, right? So that means that no collision. Doesn't matter. Okay, so circles are great, spheres are great. Let's see exactly what happens also with boxes. With boxes, it's kind of the same idea. You encapsulate your very complicated object. It might be non-convex, it can be whatever you want into this box. And then the only thing you need to do is then later just do checking with respect to segments, right? So in this case, if you have a point here, you just calculate like point to segment or maybe centroid, I don't know. There's different ways, so maybe it's a aligned box and then we use part of the objects to put here. So with this, what we gain is that there's less ambiguity. For instance, if you have a point inside this region, there's not such a problem, because it's all very tightly covering this, or even just a convex hull of your object, right? Anyway, the hierarchical is a very powerful technique. It's not super accurate, but this is something that you could be using. Let's give like a little more real example, right? So, for instance, we have these two mechanisms. They are very complex. They have a lot of degrees of freedom, right? So we have 1, 2, it should be 7, right? Yes, it also moves, right? It also rotates. This guy the same, right? So you have here a lot. Do you want to all the time just kind of create given a configuration, you want to kind of render this and then calculate if there's a collision or not? Well, there's ways for avoiding this, and I'm just going to put here like a very simple one. Let's say that we have a big sphere, okay? It doesn't have to be accurate, so maybe it's just this sphere calculated here, and then you have this sphere here calculated. And then later, if you want more spheres, the only thing you need to do is just go over the objects that you have. Okay, let's go back to red. Objects here, and for each of them we could be putting like a sphere here, a sphere here, a sphere here, and so on. Okay, so maybe this kind of hierarchical representation is going to save a lot of computations if you want to do like a coarse collision checking. The same happens here, right? So you could be doing now 2 spheres, right? So sphere 1, sphere 2, and so on, right? So at the end, the idea is this: how to represent very complex objects just with a hierarchy of very simple shapes. And by simple means that it's easy to calculate distances, right? So the simplest thing is calculate distance to a sphere, right? You just, you just need the center of the sphere, any point, and if it's inside the radius, you are inside the sphere, right? Yes. Well, let's say radius, right? Yeah. Okay. And if not, you are outside. So checking this is very fast. Checking a point to a segment, it's also a very fast checking. Okay, so now we have this hierarchy of kind of collisions. The idea is the same. So, no. Let me finish, because collision ends here. We have the hierarchy. And then I think now we are equipped to calculate all these collisions on a very fast way. And now what we do is we start with the first planning algorithm that is sampling based, right? That is called the probabilistic roadmap. Okay, so we have now fresh, what is this idea of sampling, our guarantees to find a solution. Remember, it's probably complete. It might be infinite, well, very long time, not infinite, but very long time. But still, we have like these guarantees. We have a way of expressing the configuration space, the free regions of the configuration space. And now, with all this kind of machinery, with all these guarantees, we are ready to define the first method for doing planning. Okay, so what we do is we are going to sample the C space. Okay, we have like this, we start sampling. And then for each sample, what we do is we look at the neighborhood. Okay, so we can define a number. Well, this is an hyperparameter. There's a way of relaxing this later, but on the first way of doing this, there's a parameter. What happens with this? If there's a point inside this region, then if there's a point in this region, we will see what happens. Okay, so let me sample another point. I'm going to sample here, blue, right? And then what we have is this guy here. Okay, so now what we do is we look for all neighbors that are in this region. Okay, and again, this is an hyperparameter. This could be like as complicated as you want, because remember, we are in the configuration space. If there's some neighbor, you connect it, right? And we keep doing this all the time. So maybe we come here, and then we see that this new sample is connected to two points, to this point and this point. Okay, so then we can keep doing things like this guy connected here, this guy connected here. We see that some things start arising, right? This guy here. Oh, okay. You get the idea. We start sampling. Now this guy gets connected here, and it gets connected here. Okay, I'm gonna go a little fast because. Okay. So the first step, this is what is called the roadmap. We just sample, same as we were saying before, and you can think about this threshold, kind of the guarantee for connectivity. I think you were asking about what happens when you have a configuration and another configuration and you connect it, right? So here, kind of the assumption is you can connect small enough segments, but still there's going to be little issues, right? So imagine you sample here, and then you have this that is in collision, right? So still, maybe instead of just checking like collision in each of the points, maybe you want to check the center point, or you want to check the segment, right? So this is segment check. Anyway, we kind of built the free configuration space just by this. By sampling, if we sample here, what happens? Bad, right? So this is a collision. You don't add this into your roadmap. It's not going to be included, even if it's very close to this, right? No, it's a no-no. Okay, so we keep going. We keep doing this. This is not connected here. And then at the end, once we have enough samples, and what is enough? Well, that's a little open question. Let's say that it's, yes, maybe depends on number that you give. Maybe depends on the computational budget. You want to solve this, I don't know, in 1 second or 1 minute or milliseconds, right? So this is going to give you this computational budget, and you just sample until you get there. Once you have this, let's say that you are ready for the second step. So, oh, this is not connected. And then the thing is going to be, okay, now that we have a lot of connected samples, we are just going to do graph search over this. Okay? So, okay. Yes. You see, there's connectivity. There's only like one path, like going like this. This is not, yes. Okay. So this is a way of connecting, of solving the problem. After you have all these connections, after you have built this new graph, and again, the key point here is that you are just defining this control variable, that is how much you are looking into the neighborhood, then you just do graph search. If number of samples increases, then you might find more, and then maybe you will have a way to shortcut like things, and that's a little open question, right? But the whole idea is just this. Use sample, connect things, and then later it's ready to be used for any graph search algorithm. Okay, now this, written again in pseudocode, we have the two components. Building the roadmap, that again, this is the hyperparameter that we need, number of samples. We sample the free space. Well, this is basically what I was saying, right? If it's in the free space, that means that we do collision checking, right? If it's indeed like free, then we do this, we add, we look for neighborhoods, we connect things. Maybe here we could be doing another checking if the edge is in collision or not. And we do this as many times. There's no way for us to know when to finish, right? It could be like infinite numbers. We don't know. But because we have these guarantees, the only thing we are saying is, look, we'll just be doing this for n samples. And with this, we hope it's going to be enough. Okay, and then the second way of solving this is graph search. So what do we have? We have a connected graph, right? We have, if you want, you can have values, cost, or whatever that corresponds to some quantities. Maybe it's distances, maybe it's, I don't know, other kind of related cost. If you want to do optimality here, you can as well. And then what we have is an initial condition, an initial configuration, and a final configuration. So once we have this, we have all elements. We have a graph, initial and final configuration, and we just need to apply graph search. But the difference is that it's totally different as we calculated before, that it was after discretizing the space and assuming that everything. Yes, let's go to the grid. So what is happening with the grid? The grid assumes that all these states are connected just by being close, okay? So this was the assumption. We are just adding connectivity based on closeness, right, on the neighborhood. Here, no, here we are just having a parameter that adds or doesn't add things into the graph, and we keep doing this over time. Okay, so this is a very powerful technique. Although it looks simple, it was able for the first time to solve the piano problem, right? Moving things in 6 dimensions, right? So 3D poses, moving them around. I think yes. I think the roadmaps were solved, or solving definitely they can. What is the only negative thing? Is that we do a lot of collision checkings. So then some researchers just came with this idea of let's have a lazy probabilistic roadmap. And what lazy means is that we create a graph over the C-space with sampling, okay? And then we don't check for collisions all the time. We only check for collisions as we are traversing the graph. So imagine you have your graph, there's no collision, right? In this case, it's going to be like here, I don't know, we have this, we have this, we have this, we have this. Okay, I don't know, something like this. So the first thing you do is you just go straight. Okay, I'm going to go to. And when you come here, remember, in this image, what we have is this kind of obstacle in the C space that we don't know what it is, this kind of sausage. It comes here and it says, look, no, you cannot do this. There's a collision, right? And then you basically adapt. And then you do checkings as you are traversing your graph. So you don't really need to do all of them when you are. You don't need to check for collisions when you build the graph. You only need to do them when you are traversing. Maybe there's some regret. Maybe you need to check more states when you are. Maybe you're definitely solving the graph search is going to take you more time, because sometimes you just need to change the topology of the graph and say, look, no, this connection, forget about it. No, it's not here, right? Because you have the sausage here. But in practice, you can also save a lot of collision checkings. So it reduces this number of collision checkings, and in case that there's no obstacle, it's just going to be like straight search, right? So there's nothing to worry about there. Okay, so well, in practice works well. You will not be implementing this, but we have uploaded this paper on Canvas as long as many others. So you can take a look if you're interested. Now let's go to the second most representative sampling-based algorithm. This paper has spanned thousands of publications, right? So especially early 2000s was very popular. Now these days, probably people are not publishing so much into this, but this is definitely a tool that a lot of people use, right? So, well, let's say that must know technique, right? The rapidly exploring random trees, the idea is the same. We are going to build this configuration space as we are sampling. Okay? The only difference is that it's not going to be a two-step procedure. We don't build first like full graph and then we solve it, right? What we do is there's a more clever way of adding nodes to our graph that is going to allow us to calculate a solution faster. Right? And the idea is the following. We have, let's say, this graph here, right? So this is what we have calculated. By the way, this graph is going to be a tree. So this is another difference with respect to the probabilistic roadmap. Here, we know always who is the parent. And the reason is because of this. First, what we do is we sample randomly, right? So we sample randomly over this distribution on the configuration space, okay? Let's say that our sample lies here, okay? So this is our Q run. The next step is we need to go to the tree and find the nearest node, okay? So this can take a little bit, but still, it's going to have great advantages, and you will see in a moment. So we check all these nodes here, like this one, this one, this one. Oops. And what we see is that the closest one is this one, okay? So we select this one. This is the node that we are going to expand, right? And for this, there's a function that is called extended tree. So if you imagine, we cannot really connect this random configuration with the tree because they are very far away. There's going to be problems, right? For instance, here we have collisions. And it's not a good idea. So instead of that, what we do is we do a little step. The random configuration is helping us on the direction. And the direction is set, and then the only thing we do is, let's say that we have fixed, like what is the step size that we take every time. So this is just kind of telling like what is the direction that we follow in the configuration space. And if we do this many times, it turns out that the tree is growing very efficiently, right? So for instance, you can sample over the full configuration space. And before on the probabilistic roadmap, some nodes were not connected. Right? So you cannot guarantee if you sample that you're going to have a connection. Here, you will always have a connection, right? So let's do the same thing here, right? So this guy comes here, maybe we come, and then we say, okay, you extend it here, right? The same happens here, right? So this is the closest one, you do this, and it turns out that with this way of exploring the space, we can cover the full space very, very rapidly. So that's why it's called rapidly. At the beginning, it covers the space kind of broadly. And then when we sample more and more, when we reach this density of the sequences that we were talking about, then the details become more and more clear. Okay, let me show you maybe with this example. Right, so this is what happens at the beginning. You have few iterations, and then you see that you have covered the full space. Right, you see that almost every region of this has been reached. All of them are connected, by the way. So this is just When you have more iterations, what it happens is that with this basic structure, it simply gets more and more ways of getting here, right? So for instance, here at this point is not possible to be reached, but what it would do is you just find the closest node and then expand it. You do this many times, and eventually you are going to cover the full space, right? This is a very efficient way, as I said, of exploring the space, and let's discuss a little bit about the algorithm by itself. Well, as I said, first of all, we need to sample, and then we sample from all configuration space. We have this random configuration. Then random configuration is just looking for the nearest in the tree. And then the steer function, this thing that I was talking before, it's just kind of extending things. And you should be extending, by the way, in the configuration sense, right? So every value that you have in your configuration, random configuration that you have found, you should be sampling. This includes orientation. So maybe this orientation is like this, and here you have another orientation. So you should be kind of doing this interpolation, right, between the value that you have in random and whatever value you have here. So for linear thing in XY coordinates, it's clear, so you just kind of follow the line and then create a small segment. But this is just interpolation problem, right? So you have a final value, and what you get is just a little bit of that final value. Okay. Anyway, the detail is just extend. It's just not to go like very far away. So we have this delta S. And then, well, basically we start adding edges, and we know for sure who is the parent, right? So this is going to give us like a great way of solving this later, because after we find the final configuration, the only thing you need to do is just backtrace all your parents until you get to the initial configuration, and this is your solution, right? So it's very similar to A star, where we have a table and you just backtrace all the positions. Okay, yes, this steer function has maybe physical meaning. So if we will not discuss about dynamic systems or kinematics, at least not much. But if you think about it, this is a way of propagating your system, of changing the system over time, right? And we know that, for instance, this could be like a transition function that you give the initial state or initial configuration, you give an action, and then the system is doing whatever. Maybe it has constraints, maybe it has other things. It's not like moving 3 points in the configuration space. Maybe there's this constraint. So if you have this kind of problem, the steer function is a way of solving this, right? It's helping you still to maintain these constraints into your planning problem. Okay, we'll not be working on kinematics now or dynamics, but just for you to know. So the thing is, if you do this steer function, it should be, you should be able to do this. So for instance, you cannot ask a car all of a sudden just to go back, right? If you are moving with some velocity, right? So you have inertia, you have some things. So this steer function, what it's trying to say is, or the transition function, what it's trying to say is, if you have these constraints, you can keep them while you are doing, while you are searching your graph, and still, well, you can have constraints satisfied. On problem set 2, it's going to be about RRTs. There's not going to be like this problem on kind of dynamic systems or transition function. It's just going to look like whatever is close, right? So we are just going to define a little. But for you to know that if you go a little farther and you have like other dynamic things moving and you have a transition functions, this totally applies, right? So here you will have this. Yes. Yes, this is a good question. So the RRT that is applied here is not following exactly the same idea that I have explained. So what they do is when they extend in a row. They extend multiple of these state variables here. So instead of just being this point and this point, what you see here is a lot of iteration, a lot of new nodes, right? So let's say at each extend, what they do is they add multiple nodes into the graph. So this is another way of doing. If you want more straight kind of things, then you can do it this way. With this, you maintain like good representation because nodes are close, and then you can expand things fast. The description that I explained here is you just extend once. I mean, you just steer once. In this example, yes, this is what they were doing. Like small ones, but not unique one. So well, that's a good question. If you had an obstacle here and say that you are adding these guys, maybe you are able to add to the tree 90% of the new samples. And then you get to the collision and say, oh, look, this one we cannot add because it's in collision. So this is another advantage. If you only sample one configuration and then add a single new vertex to the tree, then it's all or nothing. If you have very small ones, maybe you can add until you find a collision. It depends a little bit on the problem, but I think it's easier to start with this kind of idea. For each random configuration, you have a new nearest neighbor, right? Okay. So in essence, that's it. This was a very influential work. Still very relevant today, and the idea is so simple. It's simple now that we're explaining it, but the ideas behind is all that we have explained about density of sequences, implicit configuration spaces. There's many things that are necessary to create this, right? And still, why it's so efficient, because with this way of adding new points to the tree, it simply it facilitates the exploration of the full space, right? So this formula, it doesn't work if you apply it differently. If you sample, I don't know, random points in your tree, and then you select one, and then you extend one, you don't get the same result. So this definitely works very well. Let's talk about a couple of improvements that we can do. The first one is maybe you want to sample your goal state just to try, right? So you sample your goal state. Remember that having a random configuration doesn't mean that you will add this to your tree, but definitely it's going to go into the direction, right? So with this, with very small probability, you could have like your sequence that is combining. Sometimes very few times you sample your goal, and others you just sample the full space, right? So density is preserved, and with this you can achieve your goal also like more likely. The second is this thing that we were discussing about headed. So maybe what you want to do is for a single random configuration to have larger steps. So larger step means more nodes. Right, so we have a configuration, we have like this long segment, and all of them are connected, so you can add all of them. If you want to have like, different, more straight way of calculating it, you also need direct visibility, but you can do this as you are adding elements, maybe to the tree, if they are in collision or not. You can also change the sampling sequence depending on the boundary of the C3. So that means that you see that there's a problem in parts of your regions you are not really connecting, like for instance, let's say here. So maybe what you want to do is have a random sequence that is focused on getting a lot of configurations here in these kind of bottlenecks. It's very hard to determine, by the way, who are these new distribution, right? So sometimes, yes, it's easy to say than to do. And then the second one is bidirectional RRT. So this idea was already described for the A star. If you remember, we had also this bidirectional thing, and the problem was, okay, you need to meet at some point, you need to explore from one side, explore from the other, and at some point you are going to find. The problem here is that at some point you will need to connect both trees, so it's not trivial just saying, oh, okay, so this is connected. No, maybe this is too far away or whatever reason. But the advantage of having bidirectional is that this direction of finding these kind of traps is easy. This direction is very complicated. It's very complicated to find the exact configuration that allows you to enter this trap. So these are usually called back traps. And, well, the reason is because, yes, one direction is easy, the other is very complicated. So what are the chances of you getting here? Very small. If you go in this direction, it's easier because it's kind of steering you to the solution, even if you sample, right? So what if you have multiple of these? Well, you can do this, like 3 or more, but then things start becoming a little more complicated. Okay, let's talk about the idea of optimality. You can think about this as extra budget that we spend on samples. Maybe this is also a way for us to calculate optimality. Right. So, yes. What is the difference of adding nodes in the probabilistic roadmap and RRTs? So the RRT samples along all the configuration space. Okay? These two things are the same. Yes. The difference is the probabilistic roadmap adds this random configuration if it's close to any neighbor, right? So this is what I was saying. You sample here, and then you look for neighbors. Oh, there's a neighbor. You just connect it here. So you are kind of updating the graph, okay? But there's no other way. Maybe you sample here, and oh, there's no one. So this graph does not get updated because, I mean, yes, the graph gets updated, gets a new vertex, but there's no new edge. And maybe you come here and you sample here, and then you have 3 new edges or 4, right? Exactly, exactly. So you just look at the neighborhood that this is given, and then you connect all of them. If you do this enough times, and this is what is a little hard about this method, right? When is enough? When you have things that are really well connected, right? Well, you could be checking as you are sampling. But this, in principle, is just kind of a blind process. You let it run, and you don't know. For the RRT, you have a random sample, but then the thing that you are adding to the tree is a single new node that is kind of created thanks to this new random, but it's not the random configuration. It's this kind of projection, okay? Okay, yes, interesting. Okay. This also, I think, is going to be related with optimality because there's a payoff here. So we sample, we create our roadmap or our tree, right? It doesn't matter. And then the question is, imagine that there's a cost that we can define. For instance, you want to go faster. What is the fastest or shortest path that you can find? Or, I don't know, maybe each configuration has another cost, like stay away from obstacles, or something like this, right? The idea is that we are going to look for optimality while we are planning, right? So we'll see that for doing this, we need to slightly modify how the graphs are being created. So maybe with more samples. Here, by the way, there's no way to change the graph. Once you have edge set, you cannot undo this. You can add new ones, but you cannot undo this. And this is a little bit the problem here, right? So you see these initial conditions are dominant. If you have this good luck of, okay, at the beginning you have like line like this, it's okay, but maybe what you want to solve is this problem. You want to come from here to here. And for doing this solution is not possible, right? There's nothing that is connected. What you need to do is come here and do this. Okay, so this is kind of a problem, especially if you are looking for optimality, shorter paths, and this kind of things. So intuitively, what you need to know or what you are looking for is something that allows you to change this graph as you are exploring, right? And I'm just going to comment a couple of ways of doing this. For probabilistic roadmap, the idea is that while we are sampling, we decrease the radius of search every time, right? So we start with a very large radius, and then we start decreasing this, right? So if we do this, then at the end we'll get we'll get kind of the resolution that we need, and the path is going to be optimal, right? So in this case, there's no need to actually know. The thing for rewiring is more for the RRT. For the case of the probabilistic roadmap, the only thing we need to do is at the end there's a point where adding more connection is not helping us, right? It's not looking for, because imagine you have a radius that is very large, but actually what you want is something like this, right? So instead of this, what you want is just a small increment that is taking you here. Okay, so this is a technique proposed by Karaman and Frasoli. You start decreasing, and this has properties of optimality. Probably these are not very obvious now at first sight, but let me discuss on the second ones, because this is more, I think, clear what's happening. So as I said, what we do is we need to change the configuration of the tree. So every time that there's a new node, we are going to be using this idea of the neighborhood, same as we were doing with the probabilistic roadmap. So say that we have a region, and then the idea is, sure, RRTs cover this space very efficiently, but it doesn't mean that this is the best solution, right? So maybe your solution takes you here, and finally here, right? Maybe you're unlucky and you get a... So this is a valid solution according to the RRT. Now the thing is, when we sample a new node, what we do is we rewire connections, right? So maybe here, when we have this new connection, it connects to here, and this one connects here, right? And then we see, look, this one, well, maybe this is not a very good example. Yes. Okay, so then we might remove this edge here. Why? Because the shortest path is not this one, right? The shortest path is just going a straight line. So then that means that we should remove this edge. If we keep doing this on this kind of neighborhood, this neighborhood also decreases. It's the same decreasing function as in the probabilistic roadmap. Then at the end, what we will get is more and more straight trees, right? So at the end, all these things, so imagine you have here like this, and it's telling you, no, you don't want to connect here. Maybe, okay, you have a sample here. Maybe what you want to do is connect these guys, right? And then forget about these others, right? So at the end, you go kind of smoothing more and more your tree. Remember that this is sampling based. You are not assuming anything. But eventually, with then sequences, we should be getting optimal solutions. This, by the way, is a very weak guarantee. So optimality on infinite number of samples in practice doesn't mean that your solution is close to the optimal. Maybe it's not. Maybe it's very far away. And this idea of samples requires like too many, right? So careful with this, because sometimes, well, especially when you have higher dimensional problems, this idea of RRT star doesn't work so well. It works very well for planes, for 4 dimensions, 5, but when you go higher on dimensions, starts being a little not so. Still, it's great. Okay, other variants of RRT, right? So we have some papers, fast marching trees, informal RRT. There's also like a very strong trend now on mixing learning algorithms with sampling-based or other. So this, I would say, this is more research direction, right? How to mix these two things. So machine learning is very powerful. Maybe what you want to do is propose sampling distributions that are going to help your algorithm. Or, I don't know, there's a lot of combinations here with planning and machine learning, right? So this is just an example. But I think for me, it's kind of the topic now that will relate to research after finishing this course, right? So what is there on research now? Like, yeah, like machine learning, we cannot really ignore this. So on sampling, I think gives like a very good idea of how to improve things. You can improve things still with better algorithms, but they have been there for some time. These algorithms were published in 2012, this 2015. I don't remember well. Okay, anyway, what I have presented, I think it's very current techniques. They are used, although they were published like some time ago. They allow to solve like a whole new set of problems. So the piano problem before, it was very complicated to solve. You needed explicit representation of the configuration space in 6 dimensions. You can imagine the pain of doing this. Programming, right? Imagine if this is a problem set. Okay, you're not imagining. I am. No, so that's why sampling-based technique allow to overcome this problem. You forget about this, you forget about explicit representation, and this simply opened the door to new problems that now can be solved, right? So, yes. Let's talk a little bit about drawbacks of sampling-based, because it helps, of course, it helps what previous techniques were, mostly graph search, or maybe kind of, yes, controls, I guess. But it also has like some drawbacks. This idea I have already explained a little bit or give some hints. We go to high dimensional spaces, and this is limiting the discrete. Higher dimension spaces are limiting factor for graph search, right? So we know that we need. With more dimensions, we have much more elements, and then we cannot really find a solution. With sampling-based, what we have is, yes, we have guarantees, and then we can tackle higher dimensional problems. Okay, so this is an advantage, actually. Still, in practice, they might fail to converge, right? So you have guarantees, but these guarantees we have discussed. It's only at infinity. It's only when you have a dense sequence. When you have covered everything, then yes. But maybe you never sample regions that allow you to solve the problem, right? So there's no guarantee. There's no one that is going to come and tell you, yes, you don't find a plan. There's no way, right? So you just keep sampling and hope for the best, right? So this is kind of bad thing for very complicated configurations with very details, and this could be tricky, right? So it's something for you to think about. The rate of convergence and complexity of these algorithms is hard to establish. So for some problems, it's going to work very well. For others, you don't know, right? So this just creates a little bit problem. But on the other side, if other algorithms are not able to solve this problem for you, then this is still an advantage, right? And if we go to really high dimensional spaces, even sampling-based planners are going to have a hard time finding a solution. So why is this? Because the number of samples that you require to cover this space, to explore the space, I'm just talking about sampling and then having like properties covering the full space, not solving the planning problem. For covering the space with samples, this number of samples grows exponentially with the dimensions, right? So it's not a course of dimensionality as what we have before, but it simply becomes more and more complicated to properly cover all the full space, right? If these dimensions are meaningful. So this is another limiting factor, not as much as graph search, but still, of course, if you have 30 dimensions, it's going to be very complicated to sample exactly those that you want. Well, it's simply that the problem is complicated. Still, as I said, this is one of the most popular techniques, right, that you can find out there in planning, and I hope that after problem set 2, well, you know a little better about RRTs, and you understand a little bit more about its strengths and weaknesses. So with this, we'll finish today's class, and next Friday we have seminar, talking a little bit about collision and sampling-based issues. All right? Thank you. See you.